closer, you can see it better, or you can see more of the traffic.
Right.
But if you are farther, you can see much traffic. So.
Yes. So it's possible, but in that case, you have to enhance your alert. For example, you not only say, I think S2 is bad, I also need to give some confidence. Because, if, for example, S2 is very close to me, then I'm very confident. If it's far away, then I'm not that confident. But so far in the model, we just assume it's 1 or 0. Okay. So just give example here. Suppose this is abnormal edges I've obtained in the observability graph. Okay. So the yellow edge means that it's abnormal edge, means one node issues a lot of alerts against another one. And the white edge arrow means that everything is okay, it's normal. Okay? So from this observability graph, we can derive this inferred graph. Okay? So know that 2 and 3, there's edge, obviously because 3 has issued a lot of alerts against 2, node 2. Okay? And 2 and 5, the same reason. Note that we also have one edge between 2 and 4. The reason is because 2 thinks 5 is bad, but 4 thinks 5 is good. But they are observing the same node, so there must be something wrong between these two nodes. Okay. And I want to point out that the suspicious pair relationship does not propagate. Okay. So if you have one normal edge, for example, from 6 to 9, you cannot say for sure that either they are both good or they are both bad. Okay? Because maybe this 6 is compromised, but 6 just don't care to say something bad about node 9 here. Okay. So, and another example, for example, from 3 to 2, there's a suspicious pair, and 2 to 1, everything's okay. But we cannot say that 3 and 1 are suspicious pairs.
So does it mean among 2 and 4, you believe that one guy is bad?
Between 2 and 4, or 1 and 4?
2 and 4.
I believe one of them must be
But
bad.
it could be they're both good, just 5 is showing different aspects to one of them. So one of them thinks 5 is bad, the other thinks 5 is good.
So here we assume when you observe something, you observe the same behavior, the same activity. For example, if you say that packet dropping, then whenever you send something, I know you receive something, you should send out the package routing. So they can observe the same behavior. Okay.
But how can you observe the same behavior if they are in different locations?
Who are in different locations?
The nodes. You know.
And
like if 2 and 4 are in different locations.
But they are all close to 5, so they can all observe the behavior of 5. Because so if there's edge between say 8 and 9, that means 8 can observe the behavior of 9. Otherwise, there should be no edge between 4 and 5 at all. Okay.
Just to make sure, if a good node observes something bad, it will always be reported.
Yes.
Okay.
Yeah. So here we say a node is compromised, but maybe the node is not compromised. The node may just be defect and behave very weirdly. So we just also consider that the integrity of that node has been compromised. Okay? It may not be because of the ticker. Okay. So given the inferred graph, how can I know which one is compromised? Okay. So obviously you want to, we have the concept of value assignment. So this is basically one possible way that nodes are compromised, which is going to result in the inferred graph. Okay. So formally, it's really a partition of all the nodes in the graph. Some are good, some are bad. Okay. And there are 2 requirements. The first requirement is that a suspicious pair, S1, S2, should not belong to n good. That means if there's a suspicious pair, they cannot be both good. Okay. Another one is that the bad node, the number of bad nodes should not be bigger than your security estimation, because K is the upper bound of the number of compromised nodes. Okay. So if we find such a partition, satisfy these 2 conditions, we say it is a valid assignment. Okay. So in the previous example, maybe we can say that suppose K equals to 3. Then we may say that 2, 4, 5 are compromised, but 1, 3, 7, 8 are not. Okay. But it's also possible I just say that 2, 4, and 4, 5, and 3 are compromised. Okay. So generally, given an inferred graph, there are many possible assignments you may have. Okay. But then how can be sure that one node is compromised? The observation here is that if every assignment tells you that this node is compromised, then this node must be compromised, because no matter how you assign a compromised node, this node is always included as compromised. Okay? So we call such node form the compromised core given the inferred graph. Okay? Basically means that these nodes in the compromised core must be compromised, no matter how you're going to assign those nodes. Okay? So this compromised node is really the intersection of all the bad nodes in every possible assignment. So given the identification function, we say it is optimal if it can identify the largest number of compromised nodes without introducing any false positives. Then we say it's optimal. Clearly, it's the same as compute the compromised core, because this core contains every compromised nodes that every assignment believe they are bad.
What if the intersection is not?
So in that case, you cannot say for sure.
But still, you have that graph that says that there is a compromised node.
Yeah. So if the compromised core is empty, that means that we cannot say for sure which node is compromised. But it doesn't mean that we cannot do anything with it. We're going to discuss that later. Okay. So in our discussion, we assume a very general collusion model. That means we don't assume any specific collusion between sensor nodes. So the sensor nodes may coordinate with each other. They may not issue alerts against each other, but they may also issue alerts against each other. Okay? So basically, they can do whatever thing they want. Okay? And so in this case, the inferred graph may be of any topology. But still, we have the observation here that given the suspicious pair, at least one is compromised. So no matter what kind of collusion model they follow, this is always true. Okay? So we want to start from this point to reason which nodes are compromised.
Question?
Yes?
So when you say general model, you don't mean the most powerful adversary model.
Mm-hmm.
Because I can think that a more powerful adversary model would assume perfect collusion.
Mm-hmm. Yes. So in our paper, we actually assumed a very, as you mentioned, a strong collusion model. Basically, we assume that a node does not, two compromised nodes do not issue alerts against each other. And if they observe the behavior of the same node, they always issue alerts consistently. Okay? And now the question is that whether, even though they're colluding, whether the base station knows that or not. If the base station does not know this knowledge, then we have to assume that there's no such collusion at all. Actually, I lost some information. I cannot do better than assuming that you can do anything you want. But on the other hand, if the base station knows they always follow this strong collusion model, then I can take advantage of it. Okay? So by assume a general model, I assume that the base station has the least amount of information to inform compromised nodes. This is the worst case, actually. Because
Yeah, I can take the further discussion offline.
okay. All right. So here, let's see that suppose we have a inferred graph here. Okay. And one observation here is that, in fact, the valid assignment in the bad node of the valid assignment actually forms a vertex covering of your inferred graph, right? Because for each edge, you must assign at least one of them as bad one, right? So in that case, at least one node is going to cover one edge here. So your valid assignment, the bad nodes in the valid assignment actually is the vertex covering of this inferred graph. Then the minimum vertex covering actually gives you the lower bound of the number of nodes that are compromised in the system. All right? Okay. So now let's look at the following scenario. Suppose now I want to know whether node S is compromised.